everybody, so today I will explain for you chapter 15, which will be about the oscillation. So let us start. Firstly, what is the oscillation? Oscillation is a type of motion vary with time, regularly or irregularly. So what does that mean? For example, if we have a particle here and this particle move in this way, so we can say that this particle is moved in a straight line. But if this particle, the motion of this particle is change with time or vary with time, like this, very irregularly or very regularly, like that, for example. So we can say here that this particle is in oscillation or it's oscillate. Also, if we have a particle here and this particle move to the right, then to the left, right, left, right, left, right, left, also we can say this motion is oscillation. So because of that, what is the oscillation? Oscillation is a type of motion vary with time, is a change with time, and this variation may be regularly or irregularly. Okay. In this lecture we will focus only in the regular oscillations. And one example about the regular oscillation is the periodic motion or the harmonic motion. So what is the periodic motion or the harmonic motion? In very simple way, it's any motion that repeats at a regular interval. So I will explain those things, the periodic motion or the harmonic motion, by this example. For example, if we have here a particle and this particle is set in this position, which is the reference point is 0, and here is from the right xm, which is the largest displacement from the origin, and in the other side in the left we have minus xm. If this particle is moved to the right, then come to the left and then return back to the reference point, so we can say this particle it's do a full circle. Okay, if this motion, which is start from here, go to the right, then to the left, and then come to the reference point, if this motion is repeated, what that mean? That mean go to the right, to the left, and then to the reference point, again to the right, to the left, and then to the reference point. If this motion is repeated regularly in the same interval of time, so we can say we have a periodic motion or harmonic motion. Okay. Also, if this particle, so now we will focus only in this particle. If this particle here 0, here xm, here minus xm, so if the particle again go to the right, then to the left, and then come back, xm for example is a 1 centimeter, or no, not 1 centimeter, 3 centimeter, and here xm from the left must be minus 3 centimeter. So the highest displacement which the particle moved from the reference point is called the amplitude of the oscillation. Another important thing in the periodic motion is the frequency. So what is the frequency? Frequency is the number of the oscillation in a period of time, or in a 1 second. For example, if this particle do in 1 second 1 full circle, or we can say one oscillation. So the frequency will be a 1 hertz. Okay, hertz is the unit of the frequency. Okay, now if the particle in 1 second, in a time of 1 second, it's do more than one oscillation. For example, it's do a 3 full circle or 3 oscillations in 1 second. So we can say that the frequency F equal to 3 hertz. So what is mean by 3 hertz? 3 hertz mean that the particle do 3 full circle in 1 second. Okay, now I will give you another example. If we have here this particle again, here 0, here xm, and here minus xm. And now this particle is go to the right and to the left, then to the right, to the left, to the right, and like that it's do, for example, we will say 3 oscillations in 2 seconds or in 3 seconds. And we want to calculate the frequency. So what we will do, the frequency is the number of the oscillations divided by the time, because the frequency is the number of the oscillation in 1 second. To calculate it, we must divided the total oscillation by the total time. So will be 3 over 3, which is 1 hertz. Another example, if the oscillation is not a 3 but 9, how we will calculate the frequency? We will divide it the whole oscillation, which is 9 over 3. This will give us 3 hertz. So what that mean? That mean in 1 second the particle do 3 oscillations and 9 oscillations in 3 seconds. Another important things here is the period of the time, or the time period. What is the time period? Time period is represented by a T capital, and it is the time to do a 1 oscillation or 1 hertz or 1 full cycle. For example, if here we have this particle again, here the 0, here xm, here minus xm, and the particle is moved to the right, then to the left, then come back again to the reference point, for example, in a time which is 5 seconds. So we can say that the period time is 5 seconds. Why? Because period of time is the time to do 1 full cycle or 1 oscillation. And always the T is equal to 1 over the frequency. So for example, if we have the frequency 15 hertz, that's mean what? That's mean the particle do 50 oscillations in 1 second. Then we can calculate the time period as 1 over 50, which will be about 0.02 second. So 1 oscillations is completed in 0.02 second. If we are now returned to the book, what you can see from here, look, for example, here the particle, and this particle is repeatedly oscillated left and right along the x-axis. So this is a periodic motion. And here you can see, for example, the frequency. What is the frequency of the oscillation? Is the number of time per second that it completes a full oscillation. And here the time for one full cycle is period t, and it's given by this. Okay, now we will go to a special type of the periodic motion or harmonic motion. So in general we understand what is the periodic motion and the harmonic motion. Now we will go to a particular time of the particular type of the periodic motion, which is the simple harmonic motion, or we can write it only as SHM, mean simple harmonic motion. So what is the simple harmonic motion? Okay, so the simple harmonic motion is a particular type of periodic motion. Such motion is sinusoidal function of time t. So what does that mean? Okay, first of all, sinusoidal function, it's mean, sinusoidal function, it's mean the mode of the motion is in a shape of sine or cosine, sine t, cosine t. So simple harmonic motion is a periodic motion, okay, is a harmonic motion, but this motion is always in a mode of sine t or cosine t. To make this things easier, I will explain for you firstly the sinusoidal function, for example sine or cosine. So if we have a sine function, for example here we have that y equal to sine of t. Okay, if we will plot this function with time t 0, pi over 2, pi 3 pi over 2, or 2 pi. If we will put 0 here, sine 0 will be 0. Okay, now if I will put the time as pi over 2, which is 90, sine 90 will be 1. And for all those time, we will get this 0, 1, 0, minus 1, 0. So if we will come now to plot the function sine t, we will get this shape or this oscillations. Look here at t0 here, the sine t is 0. Okay, when the t is pi over 2 here, the sine t is 1. When the pi is the t is pi, the sine t is 0, and here 0 is here, sorry, minus 1, and here 0. So if we will plot it, we will get this type of motion. So now if the particle is moved in this way, we can say that this particle is in a simple harmonic motion. So for example, if we have here a particle and this particle is moved in this way, sorry, I know my drawing is not perfect, but if the particle move in this way, so we can say that this particle is in a simple harmonic motion. Why? Because the position of this particle is changed by a sinusoidal function, which is here, you can see here, this is a sine function. Okay, now if this particle only do this motion, so here we can say this is a 1 oscillations, or the frequency 1 here is 1. Why? Because this is a full periodic motion of the sine function. Okay, now if the particle is moved like that, what you can see from here? You can see that this motion is repeated itself. The sine function here is repeated. Why? Because this is the first oscillation and this is the second oscillation. So here the motion is repeated, and if for example the motion is continue like that, so here what you can see that the sine function is repeated 3 times. So if the sine function is repeated, for example, in the same time, for example, this is in 2 seconds and the other one also in 2 seconds, so this is all is 4 seconds and this is 6 seconds. So what you can see from here, you see that the periodic time for one oscillation is 2 seconds, because from here 2 and from here to here is 2 and from here to here is 2. So the sine function or the sinusoidal function repeated itself. Because of that, we called this motion as a simple harmonic motion. Why simple harmonic motion? Harmonic motion because it's repeated itself in the same interval of the time. And why it's simple? Because this motion is a sinusoidal, is a sine function like here. So immediately if you see this shape is for sine function. Another type of the sinusoidal function is the cosine function. So if we have here the function y equal to cosine t, and we plot the cosine t for different time, for 0, pi over 2, pi, 3 pi over 2, or 2 pi, we will get this shape. So immediately when you see this shape is represent the cosine of the t, so it's a sinusoidal function. And you can see the difference between the cosine t and the sine t. Look, the cosine at time 0, the amplitude of the motion is maximum. I mean here at t equal to 0, cosine t is equal to 1. But for example, the sine function, no, sine function when the time 0, the sine t or the sine of the 0 is 0 also, not 1. So this is the difference. This is start from the 0, the sine function, but the cosine function start from 1 at t equal to 0. So now if we see a particle and this particle move in this way, look, that way and then that way, okay, and also that way. So what you can see from here, you can see those things. Look, from here the particle, if it start the motion from here and then go and return for the same place, so this, or sorry, from here until here, this is a one oscillation. Why? Because this is a cosine t, one full cycle. Why? Because the one oscillation mean that the particle is returned to the same point. So here this is the starting point, then go to the same point in this function. So now you can see here the particle is moved like that in a cosine t, and then the motion repeat itself again. We have another oscillation here and another oscillation here. So now you can see that this particle is moved sinusoidal. Why? Because its motion is repeated itself in same interval time with cosine t. The mode of the motion is a function of the cosine t. So we can say here that this particle have 3 oscillation. Why? Because it's repeated the cosine function 3 times. So now we can summarize this idea as that the simple harmonic motion is a periodic motion, but this periodic motion must be a sinusoidal. So for example, again, if the particle move in this way and repeats the motion in this way, so you can say that this you can see that this motion is in a sinusoidal because the sine function is repeated. So if we have particle from here start move like that and like that, or for example it's move in a cosine function, that means start from here and then repeated itself. Sorry, the drawing is not perfect. So if the particle move in this mode or in this mode, immediately we can say it is a simple harmonic motion, and the function must be repeated in the same period. For example, here the cosine function, if the particle move from here and go that and go here, for example in 3 seconds, so the second oscillation also must be in a 3 seconds. So here will be a 6 second, yeah, because from here to here is a 3, and like that. So this is the simple harmonic motion, is a periodic motion, but it's move in a sine t or cosine t, not only in a random function. No, must be in sine t or cosine t. Okay, we will complete and we will go in deep to a simple harmonic motion. If we will return here to cosine t, always the motion move from a displacement or from a value, not from zero like the sine function. Sine function, no, the motion start from zero, but the cosine, no, it start from the other or from the highest displacement from the zero, and always the highest displacement from the reference point called the amplitude. Also here the highest point reach from the particle from the minus side, also the amplitude, but here the amplitude is with the minus. Here the amplitude is positive, but here the amplitude is negative. Okay, now we were clear. We can see here, for example here cosine function, it starts from 0, then go in pi over 2 will be 0, in pi will be -1, and then here will go to 0, and will complete one oscillation when the theta is 2 pi. For example, if we will come to these figures, this figure, for example, here is in the middle or in the midpoint is 0, and 0 always is the reference point. What meaning of reference point? Mean the motion is moved back and forth around it. For example, if the particle here move like that and then return, so the motion or the simple harmonic motion always move around this reference point or around the midpoint, which is always is 0. So now if we have here is the 0, and here we have the particle here. This particle, as you see, it start the motion from the xm. So the motion is not start here from 0, no, it start from the highest displacement. So now if the particle start the motion from the a value not equal to 0 or from the maximum displacement from the 0, So immediately we know that this function is moved in a cosine t. Why? Because turn here. So now we can see from this graph that from this figure that the particles start the motion from the xm. Then you can see it's go around the reference point, reach the maximum position, but from the left, here xm positive and here minus xm, and then return again to the same position. So it start from the xm, move, it's reach 0, then go to the left and reach minus xm, and then again return to the starting point, which is positive xm. And here the amplitude is the distance from 0 to the highest point reached by the particle. Here or here must be the same. For example, if from here to here is 3 centimeter, also from here to here must be 3 centimeter, but in the left or negative. And as I said before, the particle when it's moved from starting point, which is xm, go and then returned to the same point, so we can say that this particle do a full cycle, or we can say that the frequency for this motion is 1 hertz. So here, from here to here is a full motion, and the time to make a full motion is a period time, which is t equal to t capital. The period time is the time to do one oscillation. So you can see from here, in this point, the t is 0, and look, when we reach again to the starting point, the time is t, the periodic time. And because it's make one oscillation, so the time must be the periodic time at this point. Another important thing in the simple harmonic motion is to know the relation between the position of the particle and the velocity. So I will explain it here. For example, here, always when the particle here, or the position of the particle, if the particle here is in position 0, and if it's here in xm, and if here is minus xm, the particle in the simple harmonic motion must only oscillate between the xm and minus xm. It's not go far than minus xm or plus xm. For example, the particle cannot be here, for example, or here. No, only oscillate between xm and minus xm. Okay, now if the particle here in the highest displacement from the reference point, which is the position of the particle now is at xm, the velocity here must be equal to 0. Always the particle when is in the highest position from the reference point, its velocity must be 0. Why? Because it's back, and I will explain it more here. So here the velocity is 0, and here the velocity come to increase. For example, here will be a 1 meter per second or 1 centimeter per second, for example, and then here will increase, will be, for example, 2 centimeter per second, until reach the reference point. At the reference point, the velocity is maximum. For example, will be 3 centimeter per second. So you can now compare between the position and the velocity. Inverse, when the position is highest, the velocity is 0. When the position start to go to the reference point or to the 0, the velocity start increases. At the midpoint, when the position is equal to 0, the particle have the maximum velocity, which for example here 3 centimeter per second, and then the particle continue moving. What will happen to the velocity when we go far from the midpoint? The velocity again start to decrease. So for example here will be 2 centimeter per second, and then here will increase more, will be 1 centimeter per second, until it reach the highest displacement or highest position in the left from the reference point, and here the velocity will be 0 again. Why here the velocity becomes 0? Because in this point the particle start to return. If the velocity is not equal to 0 here, so that means that the particle will continue moving. But because the velocity of the particle here is 0, this things will make the particle to return again. So here the velocity is 0. Then again, when it start to move to the midpoint, the velocity will increase again until reach the maximum velocity at the midpoint, and then again until reach here to plus xm, and another again the velocity will be 0. So you understand the relation between the velocity and between the position of the particle is inverse. When the position is maximum from the midpoint, for example here, for example 3 centimeter, then the velocity is 0. When it is back to the reference point here, the x is 0 and the v must be maximum. And here, why the velocity here is have a value and maximum? Because as you see that this will make the particle to move again to here, but here no, will not move because the velocity is 0, so it will return. Okay, now I will complete the comparison. So now I will compare another things, which is the acceleration of the particle. So here x, as we say, it's equal to xm, v is equal to 0. Okay, here the x is equal to 0, the velocity is maximum, here the x is minus xm, the velocity is 0. Okay, what about the acceleration? The acceleration have a value but negative to the position. For example, in this point the acceleration is maximum but with minus sign. Why? Because here the particle is moved to here, it's back because we have the acceleration, but the acceleration is negative, and because of that the motion is go like that to the left. So you can see here that the particle at xm is go to the left. Why? Because the acceleration in this point is maximum but negative. Because of that it's back to the left. But if we will go here in this position, we say x minus x, v is 0, a is maximum but positive. Why positive? Because it will back the particle to the right. So here the acceleration is negative because it's back or move the particle to the left or to the minus. And here no, the acceleration is maximum but positive because the particle is moved to the right or to the positive x. And at the midpoint, the acceleration is 0. So now as you see that the acceleration here in the simple harmonic motion is follow the position but inverse in the sign. The x here maximum positive, the acceleration is maximum but negative. Here both are 0, and here the position minus x, and here the acceleration is positive maximum value. Okay, if we will go to this particle, for example, you can see also this particle is a periodic or a simple harmonic motion because the particle start move from here, from the highest point, then go to the reference point to minus x, and then return back. So it is oscillate around the midpoint, and because the motion start from the maximum x, so this is a cosine t. Also here is another figure or another graph. You can see here this is the displacement of the particle, and here is the time. So when the time starts from here, this is time 0 and x 0. So when the time is 0, we can see that the particle here in the maximum position then will become or will move to the midpoint here, then will go back to the negative xm, and then return back to the same starting point. So you can see from here that this is a cosine. And here you can see at xm, because the position here is maximum, is xm, so the velocity here will be 0 and the acceleration will be maximum but negative. Here, for example, in this point you can see that the particle is the position of it from 0 is x minus xm. This is minus xm. So the particle is here in the highest position but in the negative x, so the velocity will be 0 and the acceleration will be a max but positive. Okay, so now we understand this. Okay, now we can see from this figure that the particle is moved in this way. Okay, if we want to represent the position of the particle or how the displacement of this particle is a change with time, so if we want to write that, we must write it as this x of t. Why I write x of t? Because here the x or the displacement or the position of the particle is a change with t, so because of that I write it as xt equal to xm cosine omega t plus the phase or the phi. So firstly, what this function mean? This function represent the motion for this particle. So firstly, xm, what's the xm? Xm, the amplitude. Which is the amplitude? The highest displacement from the reference point. And here we choose cosine wt. Why I write cosine not sine? Because this shape is for cosine. And here omega t plus phi. What is the omega? So let us write like that, the amplitude. Okay, here the cosine, here this is the angular frequency. So what is the angular frequency? Angular frequency or the angular speed or velocity. What this term mean? The angular frequency is the change of the theta or the angle over the period of the time, or over only time, or here over a period of time. So for example, always if you will go and see the theta is a change with time, must complete one oscillation, which is 2 pi. I mean the theta for a period of the time change until reach 2 pi. To make it so, we can write here for one oscillation omega is 2 pi over t. Okay, now omega equal to 2 pi multiplied by 1 over t. So 2 pi 1 over t is f. So the angular frequency is 2 pi f. And here this is the time, and here this is the phase. What is the phase? Phase is the argument of the cosine function, and I will explain this more in the coming slides. Okay, so now here is this function which I explain it now. This is the xt, the displacement at any time. Xm is the amplitude, cosine omega t plus the phase. Omega is the angular frequency, and here this the time, and this is the phase constant, and all this this only is the phase, which is represent the argument of the cosine function. Okay, now I will explain something is very important, is that the particle must be returned to the same position at time t plus the period of time. What that mean? For example, if here we have this oscillations, for example here the time is 0. Okay, the particle must return to the same position as the time equal to t plus period of time. I mean, after a period of the time, the particle must be returned to the same point. For example, here the particle will return to the same point here. So the time here is equal to t plus t capital, and here the t here is 0. So 0 plus t is equal to t. So the time here is t. Okay, another example. For example, if we have this, okay, I will complete it. If the particle is at time equal, for example, to 1 second, is in this point, and for example the periodic time is equal to 3, for example 3 seconds. So the particle, this particle will repeat itself, or will come to the same point after a time equal to t plus t. So after t is 1 plus t capital is 3. So after a 4 second, this particle will return to the same point. And if we will assume that t equal to 4 is here, so the particle will return to the same point at t equal to 4. So those things only explain that the particle return itself after a time equal to the time at that position plus the time period. So the particle at a time t must be in the same position at the t plus t capital. So those position must be equal. The particle at time t must be in the same place after a period of time which is equal to t plus t capital. Okay, now xt, we know from this equation xt is xm cosine wt plus phi, but now we will assume that the phase here is 0. So the particle at a time t will be equal to xt equal to xm cosine omega t. So I will write it here. So here xt, it's mean xm cosine omega t, and xt plus t capital is equal to xm cosine t plus t capital. And sorry, here is the omega, this is, and here we have omega. Okay, like that. Okay, now we will go in deep to the simple harmonic motion, and I will show you different simple harmonic motion, and we will compare it together. For example, if we will go come to here we have two harmonic motion or periodic motion. One is the blue one and the other is the pink. Here is the blue and here is the pink. Okay, if we look to those two motion, simple harmonic motion, what is the different and what is the same? For example, if you will see that the blue one have a different amplitude from the pink one. Why? Because you can see that this is the blue one, the amplitude is xm from 0 to here. This is the highest position from the reference point, but the pink, sorry, have a more amplitude, or its amplitude is bigger. So because of that, the amplitudes are different. The red one or the pink one have bigger amplitude than the blue one. But if we will come to the frequency and the period of the time, for example, period of the time is the period to do one oscillation. So the first one is the start from here, it's complete one oscillation when it's reach here. The pink one also start from here and it's do a full oscillation when go to the starting point. So we can see that the oscillations or the particle have the same period of the time. Why? Because the starting point here return to itself in this point which is parallel. So both they have the same period of the time, and we know that the frequency is 1 over t. So if we have the same period, so we have the same frequency. So the frequency and the period of the time for both are the same. Okay, now we will go here. Here you can see this is the red one and this is the blue one. Both reach the same point of the amplitude, so they have the same amplitude. But if we will come to the period of the time, for example, first the pink one is start here and then return to the same point at here. So the time period is here. So the time from here to here is t capital, the period of the time. And here you can see they show you that this is the period of the time. But if we will go to the blue one is start here and then it's returned to the same point here. So the period time is here. and you can see clearly that the time period for both are different, and that means that the frequency also different because is the 1 over t. So this two waves have the same amplitude but different frequencies and periods. Okay, now we will come to the last example. Last example, we can see two simple harmonic motion. The first one is the blue one. The blue one, as you see, it starts from the maximum point of the xm and then return here to the starting point. Here, this is a cosine function. I mean this, the blue one is, we can represent it as xt equal to xm cosine omega t only, without the phi or the phase. Why? Because when we have the regular cosine curve, this is the regular cosine wave, the curve, sorry, because we know this is the cosine, so because of that we write it only as this. But if the xt is equal to xm cosine omega t minus or plus minus pi over 4. Here, this term is the phase constant, and when the phase constant appear in the cosine function and is negative, this will shift the cosine curve rightward or to the right. So you can see here, this is the pink one, because in its argument is minus pi over 4. This will make it to move to the shift. So you can imagine that the regular cosine, which is the blue, for example, like here, and when we write we add here in the argument minus pi over 4, this term will shift the cosine function to move to the right. So the shape of the cosine function will not be the regular one, but will be another one like that. This is the phase constant. When we add it to the cosine function, for example, and with minus, this will make the wave to move rightward. But if, for example, positive, this will make the cosine function to move to the left. To make this more clear, for example, if we have here x, and for example here the t, and here the xt, and we have the cosine function. Okay, now if the cosine function is only omega t, I mean the xt is equal to only xm cosine wt. Then when we want to draw the xt, which is xm cosine wt, this will be like that. For example, if I will make this as a clear or bigger, we will see this. For example, this is the normal cosine. Why? Because it starts from the position, from the highest position here, and then go to this point. But if we will add here a phase, pi over 2 minus or plus, what the phase will do in the argument of the cosine? The phase always will make the starting point or the argument of the cosine function is a change. For example, if the phase is negative, this will make the wave to move like that. But for example, if it's positive, we'll make the cosine function to move like that. So you understand now the job of the face. It's the change the argument of the cosine function. The normal one is start you can see here at a time 0 is a maximum. This is the normal one. But when we add a face, no, this will move maybe to the right if the face is negative, or to the left if the face is positive. So this is the job of the face. Okay, so we finish from the position or the displacement of the simple harmonic motion, which is, in general, it's given by x equal to xm cosine omega t plus phi. And here this is a function of t. Okay, now if we want to calculate the velocity of the simple harmonic motion, how we will calculate it? So all we know that the velocity is the change of the position with the time. So we can calculate the velocity of the simple harmonic motion by derivative the position or the displacement of the simple harmonic motion with respect to the time. Okay, so the derivative of the Vt equal to d over dt, and here we replace the xt here with this, so will be xm cosine wt plus phi equal to the derivative of the xm is a constant because it's the amplitude, it's not a function of time, so xm will be the same. Cosine, the derivative of the cosine with respect to the t is minus sine, so minus sine omega t plus phi, and inside the cosine the derivative will be with respect to t will be here omega, and here is 0, so we will multiply by omega, then we will get minus omega xm sine omega t plus phi. This is the velocity of the simple harmonic motion. So you can say here, if the position is xm cosine omega t plus phi, the velocity will be minus omega xm sine wt plus phi. So always when we want to calculate the velocity of the simple harmonic motion, firstly we will derivative the position or the displacement of this particle with respect to time. Okay, now if we want to calculate the acceleration of the simple harmonic motion, how we will calculate it? Firstly, all we know that the acceleration is the change of the velocity with respect to the time. So to calculate it, we will derivative this term with respect to time. So d over dt, vt we replace it minus omega xm sine omega t plus phi. So now this is constant minus omega xm. The derivative of the sine is cosine, so cosine omega t plus phi, and inside the cosine the derivative is omega. So omega we multiply by omega will be minus omega square xm cosine omega t plus phi. So this is the acceleration, and what you can see from here that the acceleration is equal to minus omega square xm, and here this term minus omega square xm cosine omega t is the xt, so we can replace all this with xt. So in this we can use this or we can use this. Okay, so now I will write here all thing. Xt of the simple harmonic motion is xm cosine omega t, and the velocity will be minus omega xm sine omega t, and the acceleration will be minus omega square xm cosine omega t. So here, for example, if we want to draw the displacement of the simple harmonic motion with respect to the time, because the displacement is cosine omega t, so the shape will be the shape of the regular cosine. And here is this the amplitude of the displacement. So the highest displacement reached by the particle is here xm to minus xm. Okay, now if we will come and draw the velocity of the simple harmonic motion, or for the particle which move in a simple harmonic motion, the shape is sine, and not only the sine, the minus sign. And here the wxm is the amplitude of the velocity, or the highest velocity reached by the particle. So when we will draw the sign, we will draw it in inverse. It means we know that the sine function is like that, but because it is a minus, what will happen? This will become down and this will become up. We will get this shape. Okay, and here the amplitude is the omega xm. Because of that, we write here wxm and here wxm, or omega xm. Here is the plus and here is the minus. And if we will return, the last one is the acceleration. The acceleration also a cosine, like the displacement. The difference only is that the cosine is with minus. So instead we write this the cosine like this. No, we will inverse it. How we will be like that? So look here, this is the cosine and this is the minus cosine. It's inverse. And the amplitude of the acceleration, or the highest value of the acceleration, is omega square xm. And because of that, we write here it's reach at omega square xm, and here minus omega square xm. Okay, now if we will look to all those graphs together, we can see here that at time equal to 0, the displacement is maximum xm, but the velocity is 0, and the acceleration is minus omega square xm. Okay, now if we will go here in this point, we can see the displacement is 0, but the velocity is maximum and the acceleration is 0. And all for each period we can compare together with all those three terms. So extreme value here, extreme value, mean 0 value here, extreme value here, but with different sign from the displacement. Okay, now we will go to another things, which is the force law for simple harmonic motion, or we will study or derive the relation between the force and the simple harmonic motion, or the force which causes the simple harmonic motion. So firstly we will study this, which is the linear simple harmonic oscillation in the spring. If we have a block of masses m, okay, and this block is attached to a spring, and this spring have a spring constant k. Okay, now for example, if we stretch the block, what will happen? So at the beginning the block is at x equal to 0 here. Then when I stretch the block, will move to a large distance, for example to xm, and then here will stop. When we release the block, we will see that this block will move to the left to x0, then to minus xm, then again will go to xm. If the surface is frictionless, it's mean no friction. If no friction, we will see that this block will move back and forth around what? Around xm and minus xm, and this called a linear simple harmonic oscillation. Why linear? Because it's along the x-axis the oscillation it's happening. And we know that when the block is at x equal to 0, so the velocity here will be maximum, which will be equal to omega xm, and the acceleration will be 0. Okay, when the block become here the x is equal to xm, the velocity is 0, and the acceleration here a maximum minus omega square xm. It's with minus. Why? Because it will return the block to the left, and when it's become here, the acceleration will be positive omega square xm. Why? Because it will push the block to move like this. And we know that the restoring force, which is the force which is restore the block always to move, for example if it's here, will move to the x0, then to xm, and then like that. From physics 1, the restoring force is equal to minus kx, and all we know that this equation is known as a Hooke's law. This Hooke's law. Okay, so this is from physics 1, and we know that this block now, when it's moved back and forth, the motion is a simple harmonic motion. Okay, and we know from Newton second law is that F equal to ma. Okay, because the motion here is a simple harmonic motion, so the force will appear only where? Here at the maximum, and here. I mean here F is maximum and here F is maximum also. Why? Because the force is proportional to the acceleration, and because the force is proportional to the acceleration, and the acceleration is the acceleration of the simple harmonic motion, so we can replace the A with minus omega square x m, for example, or x. Then here F will be equal to minus m omega square x. In general, I will write it, not only I will take the force at any place if we have acceleration, not only at the maximum. Okay, so I will write it like that. And we know from physics 1 that in linear simple harmonic motion, the restoring force is also equal to minus kx. Okay, now if I will divide the function, the equation number 1 to the function of equation 2, so will be F in 1 over F in equation 2 is equal to F in equation 1 is minus m omega square x, and F in equation 2 is minus kx. Now F will go to F, here is 1 equal to minus will go with minus m omega square, x will go with x, so here there remain only the k. Now k will be equal to m omega square. This is important, and from here we can calculate the angular frequency. So the angular frequency will be K over M, omega will be equal the square root of K over M. So the angular frequency for a linear simple harmonic oscillation is equal to this. And we know that the angular frequency is equal to 2 pi multiplied by f. So omega here is K over M, which is 2 by f. If we want to calculate the f, so the frequency will be equal, we divide to 2 by to 2 by, so f will be the square root of K over M multiplied by 1 2 by. And we know that the period is equal to 1 over f, so the period will be the reciprocal of the f will be 2 by square root of M over K. And this is very important. Another important point here is this, what is written in this box. They say that simple harmonic motion is the motion of the particle when the force acting on it is proportional to the particle displacement but opposite in the direction. So what that's mean? That's mean, for example, if we have here this spring, okay, and for example, if the spring now here at positive x maximum, so the force here must be also maximum. Why? Because from this equation f equal to m minus m omega square x, we can see that the force is proportional to the displacement in the simple harmonic motion, but in opposite direction. It's mean if the block is here and here is the spring, for example, x here is positive and maximum, so the force must be also maximum but must be negative. Why negative? Because the block, when it's here, the force will try to restore the block to this direction, so it will push the block to the left, so will be in minus. Here is positive, the force will be in negative because it's follow the same direction of the acceleration. And if the block here, what will happen? The force will be in this direction, will be positive, will push the block to be in the to the right. So because of that, we say that in a simple harmonic motion, the force acting on a particle is proportional to the displacement but on the opposite direction. Okay, now we will solve this equation, which is about the simple harmonic motion. Here, a block whose mass is 680 grams is fastened to a spring whose spring constant K is 65 Newton over meter. Okay, so the block is pulled a distance x equal to 11 centimeter from its equilibrium position at x equal to 0 on a frictionless surface and released from rest at t equal to 0. Okay, so now we have a block of mass 680 grams and is fastened to a spring, and this spring constant K is equal to 65 Newton per meter. Okay, here they say that the block is pulled a distance x equal to 11 centimeter. So we pull here is x equal to 0. They pull the block to become here in a distance x equal to 11 centimeter. Okay, then in a frictionless surface, that's mean no friction here, and release from rest at t equal to 0. So what they do, they release, it's mean the block when it is here at x equal to 11 centimeter, they release it. So here the time is 0. Why? Because they say and released from rest at t equal to 0. It is mean the time start here in this position, and at this position at time 0 the block is released. So the pendulum when it's released will move in a simple harmonic motion. How? It will go like that, come to the reference point 0, and then go here at x equal to minus 11 centimeter, and will go again like that, and here right and left, right and left. And here they say a frictionless surface, that's mean the motion of the block will not damped. Why? Because the friction is free, so it will move in a simple harmonic motion like that. So now we will start the first question. The first question is A. What are the angular frequency, the frequency and the period of the resulting motion? Okay, so the angular frequency, which is the omega. Omega we know from physics 1, omega is equal to k over m. Always in the pendulum, the angular velocity or the angular frequency is equal to the spring constant divided by the block mass. So will be k. The k is 65 Newton per meter over the mass. The mass is 680 gram, which is 0.68 kilogram. Then we will get the angular frequency as 9.78 rad per second, because the unit of the angular frequency is the radiation per second. Then if we want to calculate the frequency we know that the angular frequency is equal to 2 by f. So the frequency will be equal to omega over 2 pi. So 9.78 over 2 pi will give us as 1.6 hertz. And about the period is the 1 over f, which will be about 0.64 second. Okay, so we finish this those three, the angular, the frequency, and the period. Now we will go to the next question. Next question is, what is the amplitude of the oscillation? Amplitude means the maximum displacement from the reference point. So from the question, here is the reference point is 0, and the block is bolt to x equal to 11 centimeter, and here the surface is frictionless, that's mean the energy is conserved. So always we will see that this pendulum is moved from 11 centimeter to minus 11 centimeter, so the motion will repeat it between this and this. So the amplitude xm is equal to 11 centimeter. Okay, the question number C, what is the maximum speed Vm of the oscillation block, and where is the block when it has this speed? So maximum velocity is the same of the velocity amplitude. velocity amplitude. And how that? Because look, maximum velocity, it's mean the highest speed, and we know that the highest speed, for example, if we have this vt equal to w xm sine omega t plus phi, and here we have a minus. Okay, this is the amplitude of the velocity, and when we draw we will see that the velocity is like that. Okay, and always here, or sorry, because here we have a minus, so will be like that. And always the maximum velocity is here and here, and here is the amplitude, which is wxm, and here w or the omega xm, but with the minus. So the maximum velocity is always the value of the velocity amplitude, because the highest point in the velocity is corresponding to the velocity amplitude. So the maximum speed Vm will be equal to omega xm, and here without minus. Why? Because the maximum speed, we only want the value, not the direction. Okay, so the omega, we calculate the omega here, the angular frequency is 9.78 multiplied by the xm, which is 11 centimeter, which is 0.11 in meter. This is will give us 1.1 meter per second. And where is the block when it has this speed? We know that the velocity is maximum where when the x is 0 or in the midpoint. So here the x is equal to 0 and the v is maximum. So the maximum speed will be at x equal to 0, or we can say at the midpoint. Okay, now we will go to question number D. What is the magnitude am of the maximum acceleration of the blocks? So here they want the maximum acceleration. The same things. Maximum acceleration mean the acceleration magnitude. The acceleration amplitude. Why? Because the acceleration is equal to a minus omega square xm cosine omega t plus phi. Okay, and when we will draw it, we will get like that. So the maximum value here is always the omega square xm, and this is the amplitude. So the acceleration will be a maximum at the amplitude. So we will write that am, which is the maximum acceleration, is equal to omega square xm. The omega is 9.78 square multiplied by xm, which is 0.11. Then we will get 11 meter per second square. So this is the maximum acceleration. Okay, question number E. What is the phase constant for the motion? So we have this xt equal to xm cosine wt plus phi. Okay, they want this, the phase constant. Okay, so we can see from this figure that at t equal to 0, the xt, when t equal to 0, it's mean the x here is equal to 11 centimeter. Okay, now how we will use this to calculate the phase. Okay, here in this question xt equal to that, so when xt equal to 0, it's mean xm cosine omega, and here t equal to 0, so this is will be 0 plus phi. Okay, now x at t equal to 0, it's equal to 11 centimeter, which is the xm. So we can write it as 11 centimeter, or only we can write it as the xm. And here xm cosine omega multiplied by 0 is 0, so here will remain only the phi. This will go to this, 1 will be equal to cosine phi. Now we will take the shift cosine for both sides, so here cosine minus 1, cosine minus 1, this will go with this, so here phi will remain. The shift cosine of 1 is 0, so the phase constant for this motion is equal to 0, and 0 what? 0 rad, because this is the angle. And here phi is not only just be a 0, also it can be any integral of 2 pi. Why? Because cosine 0 give us 1. Also if we say cosine 2 pi will be also 1. Okay, if we say cosine, for example 3 multiplied by 2 pi, I mean integral here, will be also 1. So the phi will be 0 or any multiple of the 2 pi. The last question is what is the displacement function xt for the spring block constant system. So they want the displacement function, so they want to write the answer in a function term. The displacement function xt is equal to xm cosine omega t plus phi. Okay, now xt equal to xm is 0.11 meter, we know it. Cosine angular frequency is a constant, which is 9.8 rad per second, multiplied by t plus phi, and here is all is, and here this is with the meter, so we can write it like that. So xt will be equal to 0.11 cosine 9.8 t, and here this is the phase constant is 0, so this is the displacement function for this spring block system.